Okay, so I hope people can see my screen.
Yes.
Yes.
All right, so today I'm going to introduce gravitation, and I hope everyone is doing very well. I will not, because I will not be seeing, I will not be direct on the class. So whenever you find any challenge, you just say, "Excuse me, sir," and then you start speaking. So because I will not always be checking out to see. So just in case you have a concern during the lesson, in case you have a problem, you have a challenge during the lesson, just say, "Excuse me, sir," and then you speak. So I really don't like this. So I was saying, whenever you find a challenge along the way, just raise your concern so that we move on smoothly. So today I want us to introduce gravitation as our first unit in A level. Of course, before I introduce or before I talk about gravitation, I just want to let you know that we are now in A level, and A level being the most important topic, the most important paper, a lot of emphasis and a lot of time will be given to this course. A level comprises of two papers. We have what we call a physics. We have physics 979702. This is the physics we are offering. But A level content has two papers. We have 9702 stroke 52, or it can be 52, 51, or 53 depending on the school, or we simply call it paper 5. And then we have 9702 stroke, it can be 41, 42, 43, we simply call it paper 4. Now paper 5 is A level, it would be like alternative to practical, but because it is compulsory, so I can't say it is like an alternative to practical. But in paper 5, we actually study, in paper 5, we don't actually, we are not supposed to study. But in paper 5 is like an exam where you put yourself in a practical situation, design an experiment, explain how you'll perform the experiment, explain the apparatus you'll use for during your experiment, how you'll analyze results, how you'll make them reliable, how you'll improve your results, and so on and so forth. This is actually paper 5. So that is still A level, advanced level. So you will realize that, of course, most of us may not easily plan an experiment, may not easily think of which apparatus could be used during a practical situation. But for those of us who studied paper 6 in IGCSE, at least I tried to give you a clue. I remember. And I told you the last question in paper 6 IGCSE, which was asking you to plan an experiment, is now going to be a full paper in A level. So at this point, you are going to find paper 5 having two questions. Question number 1 will be actually planning an experiment for 15 marks. So you will plan an experiment. We shall do some examples, and I'll try my level best to help some of you to develop skills of planning an experiment. However, planning an experiment will require that actually you condition your mind to always think independently. There will be a second question in paper 5, which is going to be called analysis. Analysis and evaluation means you are going to perform an experiment. You are going to, okay, the experiment has been performed, but then the results are given and are incomplete. So you are going to assess, you are going to analyze the results given, you evaluate them so that you can be able to actually come up with conclusions. That's what we call analysis and evaluation. That is question number 2. Each of these questions carries 15 marks, giving us a total of 30. So that is A-level paper 5. What we are talking about today is A-level paper 4, which is out of 100%. It is exactly out of 100. And this paper, when you raise 35%, even the devil cannot stop you from passing physics. But be informed that raising 35 does not come easy. You can't be sleeping and you think you'll wake up and raise 35 in paper 4. Not at all. Paper 4 requires a student who is self-driven, interested in learning, who is not going to be followed up every time to study. If you're not such a student, you are lucky you can request the school to allow you repeat grade 11. Don't say I never told you. For those who are willing to learn and want to do this once and for all, you can start now. Paper 4 is the most important paper in ASA level because the moment you raise 35 out of 100, it means you are good enough to go. So you must take this as a very serious paper. So in this paper, we are going to see units such as motion in a circle. We shall see gravitational fields. We shall see electric fields. We shall see magnetic fields, alternating current. We shall see capacitance. We shall see temperature, ideal gases, thermodynamics, oscillations, quantum physics, nuclear physics, medical physics, astronomy, and cosmology. So there are almost 14 topical areas, and some of these areas have already been uploaded on YouTube. For example, ideal gases have been uploaded on YouTube, thermodynamics have been uploaded on YouTube, and I think temperature will also be uploaded soon. So some of these units you can also learn them on your own at home because I've tried my level best to explain them and upload the videos on YouTube. So you can also learn them at home on your own. So today I don't want to waste much time. I want to rush to first. I want us to rush to gravitation. Let me first go and I'll have to first go and so please, this is just a caution. When I start class after 10 minutes and you come in after 10 minutes, after 10 minutes, don't just come because I will not have time to keep on checking who has just joined so that I admit them to the class. You have 10 minutes to join the class. 10 minutes to join the class. If you can't do that, then don't join the class after 10 minutes. I don't have time to keep waiting for people to join the class. Thank you. 10 minutes. I wait for 10 minutes for people to join the class. After 10 minutes, I can't be admitting people into the class. Okay, so let's go back to our gravitation. Let's go back to our gravitation. So to begin with, under gravitation, we are going to begin by looking at what we call gravitational fields. So at this point, you might be asking yourself, what is a field? Of course, I always hear people in everyday spoken language referring to a soccer pitch as a field. Could that be the same meaning of a gravitational field? I think right from primary, you have been talking about the force due to gravity. And at this point, you and me are aware that we live in what we call the Earth's gravitational field. So the first question you would ask yourself is why is it called the Earth's gravitational field? Why is it called a field? You must have noticed that if a fruit ripens on a tree, it on its own falls down. Why doesn't it fall up? Or why does it have to fall down? So this is all around the concepts of gravitation. We live in the Earth's gravitational field. Before we understand what a gravitational field is, what is actually a field? So what is causing the ripe fruit to fall downwards when it is ripe? Perhaps there is a force which we normally call force of gravity continuously acting on that fruit even before it ripes. That when it ripes and loses support, the force of gravity overpowers the support and the fruit falls down. So it seems like when an object is in a field, it is most likely experiencing a force. Therefore, we are going to simply say that a field is a region of space where an object, where a force can be experienced, where an object experiences a force. This could be having, or this force could be having certain properties. For example, we live in a gravitational field. We live in the Earth's gravitational field. What properties does this force that we experience have? This force only acts on us because we have mass. So any object which has mass experiences a force due to the gravitational field. That's why when a fruit is ripe, it will fall downwards. When a plane loses support, when a plane loses, I don't know, when the engines break down, the plane will have to come back to the Earth's surface simply because there is always that force we are experiencing due to our mass. Think of a situation if we had an object, if it therefore exists, that is extremely massless. Let's think about light. I don't want to look at light as an object, but because light is massless, we can't say that it experiences the gravitational field. People talk about black holes and so on and so forth, but that would be a concern of another day. So, does light also experience a gravitational force or a force? Because if it comes into our gravitational field, well, light is massless, therefore, it is not actually experiencing the force due to gravity in our field. So we live in the Earth's gravitational field, therefore, we experience a force which is depending on our masses. So that region of space where an object experiences a force with certain properties is going to be called a field. We shall not be referring to the field that we talk about in school. However, we are going to discuss three areas or three types of fields. These are going to be independent topics, but I can't fail to talk about them now. Number one, the first one has already been talked about. We have said we are going to be looking at gravitational fields just today. Of course, after gravitational fields, we may look at another field, but we are saying we live in the Earth's gravitational field. We live in the Earth's gravitational field. So it's like when an object has a mass, it experiences a force due to the gravitational field. Any object above the Earth's surface experiences a force due to the field of the Earth. So it appears as if the gravitational field only affects anything that has mass. The gravitational field affects anything that has mass. So any object which has mass will experience a force when it is in the field of another object. We experience a force because we are in the field of the Earth. So anything which has mass is going to be affected or will be influenced by the gravitational field. So that's one of the fields that we shall discuss. I'm saying there is always a region of space around a given mass where a gravitational force is experienced. Any point around the Earth's surface, a mass will experience a force. That means even if we have two masses close to each other, one mass experiences a force due to another mass. And of course, the other mass also experiences the same force due to the first mass. So the region of space around a mass where a force is experienced is what we are going to call the gravitational field. A region of space around a mass where a force is experienced is going to be called the gravitational field. Later on, in another topic, we shall talk about the electric fields. Of course, electric, that is dealing with charges. We know that electric fields deals with charges, as we saw in, no, we didn't see this in AS because it was removed. It was actually pushed to A level. But in IGCSE, those who studied some IGCSE, you have some ideas about electric fields. You talked about electric field patterns. You were actually talking about charges. You mentioned the law of charges, where you said like charges repel, unlike charges attract. So it's like in electric fields, we are going to talk about uh, a region of space where, or a region where anything that has charge causes a force or experiences a force. So it means in electric fields, or we shall see that electric fields affect anything that has charge. And I think that is what you mentioned um, in IGCSE. Anything that has charge is affected by electric fields. The last type of fields that we shall talk about is going to be called the magnetic fields. And the magnetic fields, for us who studied some magnetism, and for those that I taught in IGCSE, I think with our last unit must have been electromagnetic induction. And under electromagnetic induction, we saw that a magnetic field could create a current or an EMF, and a current could also create a magnetic field. That's why the unit was called electromagnetic induction. So, when somebody talks about magnetic fields, is either referring to magnets which can cause a current, or is referring to currents which can cause a magnetic field around them. That means magnetic fields affect either permanent magnets or electric currents. So magnetic fields affect permanent magnets, or it affects electric currents. We know from IGCSE, for us who studied IGCSE, we know and we are very much aware that if we have a north pole somewhere here and we bring another north pole somewhere here, there is a force of repulsion in here. That means when this tries to come in the region of space around the other north pole, there's a force of repulsion. So this area here around the poles of a magnet is what we are going to call the magnetic field. Also, for us who studied IGCSE, we remember there is a magnetic field caused by a current carrying conductor. Those who remember, I remember I'm the one who taught this very well. So if a current is a conductor or a wire is carrying a current, for us who studied IGCSE, we mentioned that there is a magnetic field around the wire which was actually concentric circles. We saw that these were concentric circles around the wire. So it means there will be a force experienced around a current carrying wire or a current carrying conductor. So that force is going to be due to the magnetic field which is created around a current carrying conductor. So there is a magnetic field around permanent poles of magnets. There is a magnetic field around a wire which is carrying current. So we expect to experience forces around those points. So we shall be exploring these three fields. We shall see the gravitational field, we shall see the electric field, and the magnetic field. So these three types of fields may have similar properties, but they will have some important differences. Maybe we can try to explore some of them later on, but for now, um, I want us to talk about key definitions and concepts that will be common to all the three types of fields that we are going to study. But as we study these three types of fields, you should be able to actually compare them and note the differences carefully, because the differences will help you to qualitatively understand the three fields. By the way, these fields, unlike the AS topics, these units are going to be relatively wider. These units are going to be relatively wider. To begin with, we know that the Earth's gravitational force extends even beyond its surface. For example, the moon stays in its orbit. The moon stays in its orbit because of the Earth's gravitational pull. So it means the Earth's gravitational field extends far away, even into space, where we may not easily be reaching. So the Earth also orbits the Sun, or even other planets also orbit the Sun. And we believe there is a natural force between these planets and the Sun. And this force is expected to be responsible for holding these planets in their orbits around the Sun. So this is actually what we are going to call the gravitational force. This force is experienced when one mass is in a region of another mass. When one mass is in a region of another mass, it experiences a force. The moon is in the region of the Earth's gravitational field. That means the gravitational field of the Earth extends as far as to the moon, causing that force of attraction between the moon and, and the Earth. By the way, the gravitational pull of the Sun is just enough to keep all the planets in their orbit around the Sun. So there is a natural force. Later on, we are going to see that this force is only attractive. There is a natural force of attraction between two masses. There is a natural force of attraction between the Sun and all these planets. And that force is responsible for keeping all these planets in their orbit around the Sun. Does it mean if planets orbit the Sun, then what is happening to the Sun? Is it also orbiting the planets? Maybe we shall explore that more in under a unit called astrophysics and cosmology. So for now, we are saying that the region around a mass where the gravitational force is experienced is actually the gravitational field. We are also saying that gravitational attractive forces between two objects only affect their motion when at least one of the objects is very massive. So somebody might be wondering, a ripe mango falls downwards. Why can't the earth fall upwards? Why is it that if I place two pens on my table, I don't actually see that there is a force of attraction between the two, yet the two pens are masses? So it is very important for us to note there is always a natural force between two masses. Actually, according to Isaac Newton, that force is attractive. There is a natural force of attraction between two masses. If that force was not always attractive, you would have seen a ripe mango when it is ripe, it falls upwards instead of falling downwards. It is falling towards the earth. It means there is a force of attraction which was existing between the mango and the earth. So I am saying, if I have two pens, if I have two pens on the table, let's have two pens or two simple objects on the table. We have object A and object B. Somebody may be wondering, if there is a natural force of attraction between two masses, this is a mass, this is a mass. Why don't we see object A or object B moving towards object A? Why don't we see object A moving towards B or object B moving towards A? So we are saying the gravitational force of attraction between two masses is only effective if one of the mass or if one of the object is extremely massive. By the way, the Earth's mass, I think the Earth has a mass of approximately 6.0 times 10 power 24 kilograms. This is the mass of the Earth. That value will come several times. The mass of the Earth is approximately 6.0 times 10 power 24 kilograms. Now compare with everyday objects. Compare with everyday objects. Lisa, are you present?
Yeah, teacher, I'm present.
What is the estimate? Give an estimate for the mass of an apple.
The mass of an apple.
Yes.
Can it be like 75 grams?
75
Yeah,
grams.
yeah.
75 grams. Vanessa, what do you think?
I think around 150 grams to 200.
That is the mass of an apple?
Yeah.
Naomi, what do you think?
I think it's like 3.0 grams.
3.0 grams. Wow. Asen, what do you think?
0.3 grams. Also.
0.3 grams.
Yeah.
Wow. People are giving funny estimates. Okay. Now compare the mass of an apple with the mass of the Earth. I am saying the force of attraction or the gravitational attractive force only affects motion of two objects if one object is extremely massive compared to the other. So if you have two pens on a table, assuming A is one pen and B is another pen, you notice that their masses are relatively small. And of course, other factors come into play. These two masses could still be experiencing the force due to the gravity because as long as an object has a mass, there is a gravitational field around it. And why don't they move towards each other? There are other factors that we can talk about. One, perhaps the force due to friction between the table and the masses is greater than the force of attraction between the two masses. That could be the reason as to why they are not moving towards each other. But we are saying the force of attraction is going to be very effective, or its effect will be seen in form of motion if one object is extremely massive compared to another. One object is completely massive compared to another. So if you leave the Earth's surface, for example, and you get close to the sun, then chances are high that you'll move towards the sun rather than coming back towards the Earth, because the sun is very massive compared to the Earth. Any object in the Earth's atmosphere falls to the Earth's surface because most objects above the Earth's surface have a smaller mass compared to the mass of the Earth. So it's like the Earth attracts all objects. It never repels any object. That's why we are saying the gravitational force between two masses is always going to be attractive, but it only affects the motion of the two objects when at least one of the objects is very massive. And this explains why we are aware of the force that attracts us and other objects towards the Earth. In other words, it's because the Earth is very, very massive. The Earth is very, very massive. To sum this up, the region around a mass where the gravitational force is experienced, we have called it the gravitational field. Any region around a mass where the gravitational force or where a force is experienced or where a force is felt is going to be called the gravitational field. And according to Isaac Newton, all masses create a gravitational field in the space around them. All masses create a gravitational field in the space around them, including yourselves. Of course, this could seem surprising because I have just shown you that if you have two small objects on a table and there is a force of attraction between them, you may not see the objects moving towards each other. But I have explained that this is because the attractive force between these two objects could be very small or very tiny. It could be very much smaller than the frictional forces that opposes their motion. Two tiny objects may not move close to each other because the attractive force between them could be very small and very much smaller than the frictional forces that oppose their motion. The gravitational force between two objects only affect motion of objects if and only if at least one of the objects is extremely massive. So this is an introduction to gravitation. So the mass of the Earth is approximately 6.0 times 10 power 24 kilograms. Some of these constants should become now part of you in gravitation. Of course, they are always given, but me, I always forget. So the mass of the Earth is approximately 6.0 times 10 power 24 kilograms. You see that this, of course, because it's raised to a power of 10, it appears to be small, but it is a very big value. That is a very, very big value. So let's now understand in details the gravitational field. Let's understand the gravitational field. How do we represent a gravitational field? Just like we did in IGCSE, we talked about representing an electric field. We were using lines which had arrows. We were using lines which had arrows, and we were saying, or we saw that the lines point in the direction of the field. And in fact, they were pointing, depending on the charge, the lines were either pointing in the direction of the force, or they were pointing in the direction of the opposite to the force, depending on the charge. That was in electric fields. But of course, in the gravitational fields, because the force between two masses is always attractive, it means the field lines will always point towards the mass. The field lines are always going to point towards the Earth. We know that at any point on the Earth's surface, any object is attracted towards the center of the Earth. So what does that imply? It appears as if the gravitational field due to the Earth is going to be uniform, and it's like the field lines are turning towards the center of the Earth. It appears as if the field lines are turning towards the center of the Earth. I don't know whether when you go towards a hole dug somewhere, I don't know whether when you tend to fall or to stand above the hole, I don't know whether you fall downwards or you fall upwards. But however deep the hole is, you'll always fall downwards. It's like you are trying to move towards the center of the Earth. So it means at any point around the Earth's surface, it's like the gravitational field is pointing towards the center. The Earth tends to attract all objects towards the center. Because the Earth is sometimes assumed to be spherical, yet it could be elliptical because it bulges at the equator. The field lines, to show that there are field lines in all parts of the around all parts of the Earth, then these field lines are going to be radial. We represent a field with lines. Because the Earth is many times assumed to be spherical, even when it is not spherical, it means if there are field lines from all points of around the Earth, then these field lines could appear to be pointing towards the Earth. Why do we draw them pointing towards the Earth? Because the Earth attracts everything towards its center. So these field lines should be pointing towards the center. It attracts everything towards the center. So any other mass, for any other mass, the field around it, if the mass is spherical in nature, the field around it comprises of field lines which are pointing towards the center. So this is how we represent a gravitational field. Note that it is not only the Earth with a gravitational field. Any other object which has a mass has a gravitational field, because a region of space where a mass experiences a force of attraction due to another mass is what we call the gravitational field. The force is always attractive. This force is always attractive. So what did we see from this representation? You notice that as you move close to the center of the Earth, it's like the field lines are coming close to each other. The distance between the field lines becomes smaller as you come close towards the center of the Earth. As you move away from the Earth's surface, you notice that the field lines are moving apart. It's like the field lines are actually moving apart. The distance between the field lines is increasing. From IGCSE, we mentioned, number one, that the direction of these arrows shows the direction of the gravitational force, or the direction of the force. Number two, we say that the spacing between the field lines gives information about the strength of the force or the strength of the field. This is what we are going to call the gravitational field strength. This is what we are going to call the gravitational field strength. The separation of the field lines gives some information about how strong the field is. Now, these field lines are said to be radial. The Earth's gravitational field is radial. What does that mean? It's like the field lines are terminating or appear to be terminating towards the center of the Earth. That's why we are saying the Earth's gravitational field appears to be radial. I don't want to say it originates from the center or the field lines originate from the center. Because the Earth appears to attract all objects towards its center, then the field lines appear as if they terminate towards the center of the Earth. That's why we are calling that to be radial. Some people may not have seen the word radial in their lifetime, so I have to write it very clearly. So the field lines are said to be radial. It's like they radiate, but they radiate towards the center. They are said to be radial. They radiate towards the center. That means close to the center of the Earth, the gravitational field strength, which we shall later on represent by the letter G, which you wrongly or you normally call acceleration due to gravity, we shall later call it gravitational field strength. It appears as if the field is stronger closer to the center than as you move away from the Earth's surface. I think this makes sense. When you move away from the Earth's surface, scientists believe that when you go far away from the Earth's surface, you tend to be weightless. If we believe that weight, W, is given by m times g, if the mass of the object does not change, as you move away from the Earth's surface, the field strength decreases because the field lines move further apart. If this decreases, it makes sense for this to also decrease. Therefore, the field lines are close to each other towards the center. That means, or this implies, that the field is stronger as you move close to the center of the Earth. But as you move away from the Earth's surface, the field becomes weaker and weaker and weaker. The field becomes weaker and weaker and weaker. Now, does it mean when you are on the bottom floor, that is, I don't know which grades are on the bottom floor on the Cambridge block. When you are actually, let's say when you are on the CIE coordinator's office, Madam Rachel, does it mean your weight is different from that when you are in your grade 12 class? Now, this is the demonstration I have on the right. Does it mean you are most likely going to weigh less when you go to the top floor of your Cambridge building as it is at the bottom floor? Maybe, but it may not be. There may not be a very big and observable difference. Then what happens? On the scale of a building is very, very small compared to the Earth as a whole. On the scale of a building, the field lines are very, very close to each other that they appear almost parallel to each other. On a scale of just a building, in comparison with the Earth, the field lines appear very close to each other. Since they never cross each other, they appear to be almost parallel to each other. So they appear as if they are evenly spaced on the scale of a building, because the building is very small compared to the Earth. So on the scale of a building, the field lines appear to be almost parallel to each other. And if field lines are equally spaced or parallel to each other, then it means the field strength or the force is going to be constant. If the field lines appear to be parallel to each other, as demonstrated in this case on the scale of a building, it means the field strength, which we are later on going to call G, is going to be almost the same around the building. That even if you measure your weight on the bottom floor, you will get the same weight when you move to the top floor, because the field strength is almost the same on the scale of a building. So, the gravitational field in and around a building on the Earth's surface shows that the gravitational force is directed downwards everywhere. And because the field lines are almost parallel and evenly spaced, the strength of the gravitational field is going to be the same at all points in and around the building. So I am trying to say that this means that your weight on the bottom floor is going to be the same everywhere on the building, because the gravitational field around the building will be almost the same. Your weight does not get significantly less even when you go to the 10th floor. Perhaps your weight may significantly change if you go several kilometers away from the Earth's surface. We may not have such very tall buildings several kilometers away from the Earth's surface. Maybe somebody will say, how about the tallest building in Dubai? Is it what is the name of that building? Isaiah, do you know the name of the tallest building in Dubai?
Not sure. I don't know that.
But Isaiah, what do you know? Babas, do you know the tallest building?
No.
Wow, you're very interesting students. What do you normally do with your computers? I always see you on your computers, and I don't think you are always studying. What are you always trying to research about? Issa, what do you normally research about on your computer?
Teacher, how can I go searching the tallest building in
No,
country?
I mean like what do you always do on your computer every day? Because I always see you on your computers normally.
We read our notes which we have and use YouTube to revise.
Okay, so I'm saying your weight will not significantly change even when you go upstairs, because the change in height is still very small for the value of the gravitational field strength to significantly change. I am saying that on the scale of a building, the building is very small, and compared to the Earth as a whole, the field lines are very close to each other, and since they never cross each other, they appear almost parallel to each other. And since they appear almost parallel to each other, it appears as if the field strength caused or due to these field lines is almost the same. So from the diagram of the Earth's gravitational field, I want you to note that all objects are attracted towards the center of the Earth. This is going to be true even if they are below the surface of the Earth. Even if the object is just below the surface of the Earth, it is always attracted towards the center of the Earth. And I want you to also note that the gravitational force gets weaker as you go further away from the Earth's surface. and we are saying this is shown by the separation between the field lines. So the field lines have great significance. So let's summarize this in another slide for these field lines. So the field lines show two things, as we have seen in the previous slide. Number one, the arrows show the direction of the gravitational field, and we have seen that for the Earth, the arrows point towards the center of the Earth. We say they are radial towards the center of the Earth. They are radial towards the center of the Earth. Number two, so these field lines have showed you the direction. The arrows show the direction of the gravitational field. Therefore, they show the direction of the gravitational force on any mass which is placed in the field. Any mass in the Earth's gravitational field is going to move towards the center of the Earth. Number two, the spacing of the field lines, we have already seen that it indicates the strength of the gravitational field. The spacing of the gravitational field indicates, the spacing of the field lines indicates the strength of the gravitational field. We have seen for the Earth, in particular, on a large scale, close to the Earth's surface, the field lines are closer, so we say the strength is higher. As you move away from the Earth's surface, the field lines move apart, so the strength is smaller. But again, we have already mentioned that on the scale of a building, in comparison to the Earth as a whole, the building is very small. Therefore, since the field lines never cross each other, they will just be parallel to each other. The field lines are parallel to each other, and if the field lines are parallel to each other, it means the strength of the field is uniform or it is constant. The strength of the field is going to be considered to be constant or uniform. In IGCS, we represented the uniform electric field with the parallel lines, those who remember. Parallel lines indicate a uniform electric field. We did the same in electromagnetic induction, those who remember. So when the field lines are parallel, it means the field is constant. The strength of the field is constant, or it is uniform everywhere. So on the scale of a building, we can't say that the field strength is weaker as you go on top of the building or larger as you go to the bottom of the building. If that difference is to be detected, you must move several kilometers away from the Earth's surface. Since we don't have such buildings which are several kilometers away from the Earth's surface, then we can say on the scale of the building, the field strength is uniform. I want people to note that very, very carefully. Okay, so we shall be therefore defining gravitational field line as the direction in which a mass would move in a gravitational field. Because we have seen that if this is the Earth, the field lines point towards the Earth, towards the center of the Earth. If this is the Earth, the field lines point towards the center of the Earth. That means any mass in the region of the field of the Earth will move towards the center of the Earth. Therefore, when somebody talks about a field line, is referring to actually the direction in which this mass would move if it was in the Earth's gravitational field. A gravitational field line is going to represent the direction in which a mass would move in a given gravitational field. We are also going to define an electric field line. We shall later on define a magnetic field line. Since we are defining a gravitational field line, then we must be referring to a mass. When we define an electric field line, we shall be referring to a charge. And when we define a magnetic field line, we shall be referring to a magnetic north pole. So, a gravitational field line is the direction in which a mass would move in a gravitational field. That is what we are going to call the gravitational field line. I hope I have tried my level best to give this introduction. So we have already said the Earth is almost a uniform spherical mass. Some people say it bulges a bit at the equator. I think that is true geographically. Those doing MPG can tell us whether it is true. It bulges a bit at the equator. I think that is true because from my small geography, that's what I saw. So the Earth bulges slightly. The Earth bulges a bit at the equator, and we are saying that the gravitational field of the Earth is as if its entire mass was concentrated at its center. The gravitational field of the Earth is as if its entire mass was concentrated at its center. We have already seen that the field lines are radial and they tend or they appear to be pointing towards the center of the Earth. What does that mean? It appears as if the entire mass of the Earth originates or is concentrated at the center of the Earth. So if you are observing or if you were to observe the Earth from space, as far as the Earth is concerned for observations taken from the space or far away beyond the Earth's surface, then you would get an impression as if the Earth is behaving like a point mass, because we are saying since the field lines are radial and are appearing to be terminating towards the center, it appears as if all the mass of the Earth is concentrated at the center, because every object in the Earth's gravitational field is tending towards the center. So for an observation far away from the Earth's surface, you would get an impression that maybe the Earth is a point mass. The word point in science is going to refer to small point. So the Earth is behaving or is being treated like a point mass. We saw a point source of light in light for us to study the IGCSE. It was referring to a small source of light. So if you were to observe the Earth several kilometers away from the Earth, you would get an impression that the Earth is a small mass, a point mass. But we shall later on redefine what we mean by two-point masses. Also, we have already seen that the gravitational field in and around a building on the Earth's surface shows that the gravitational force is directed downwards everywhere, and the strength is the same at all points around the building. That's why I used the word uniform. Because the field lines were almost parallel to each other, the field would be referred to being uniform or constant, because the field lines are parallel to each other. And it's for this reason that I mentioned that your weight will not change significantly even when you go upstairs, because on the scale of a building, the change in height is very small to cause a significant change in the value of gravitational field strength. But do not forget that as you go far away from the Earth's surface, the field lines tend to move further apart. And as they move further apart, it implies that the field strength also decreases. In summary, these are some of the points we need to note in summary. Number one, the force between two masses is always attractive. And I mentioned the Earth cannot repel any object in its atmosphere. Even the largest Airbus, when the engine is failed to operate, it will come towards the Earth's surface. The Earth does not repel any object in its atmosphere. So we conclude that the gravitational force is always attractive. Whenever we have two masses, the force between them is always attractive. By the way, you remember I mentioned in one of the units that we studied that there are four fundamental forces of nature. Apart from gravitational force, can somebody give me a second force?
Electric,
I beg your pardon?
magnetic force,
Magnetic force. Not really. There are four fundamental forces of nature. One is gravitational force. The second one,
Upward.
did I hear somebody say upthrust?
Yeah, I talked about up first.
Not really. There are four fundamental forces of nature. The first one is gravitational force. We mentioned them. Isaiah, do you have any?
Not sure. Not this time.
Electromagnetic force.
The second one is electromagnetic force. We are remaining with the two which we mentioned in particle physics. The third one,
Weak force.
we don't have weak force. There are two
Strong
forces we
nuclear
mentioned,
force.
and there are two forces we mentioned in particle physics:
The strong nuclear force and the weak nuclear force.
the strong nuclear force and the weak nuclear force. These are the four fundamental forces of nature. The strong nuclear force, we mentioned it under hadrons. The weak nuclear force, we mentioned it under leptons, the force which was responsible for beta decay. Then, in addition to those two, we have this, the electromagnetic force and the gravitational force. These are said to be the four fundamental forces of nature. So, we are also saying that the Earth's gravitational pull acts towards the center. We have already established this. And the Earth's gravitational field is radial. I'm saying it is radial since all the field lines spread out radially as you move from the center of the Earth. Somebody is coming after 12. Go to hell. The field lines become less concentrated with the increasing distance from the Earth and more concentrated as you move towards the center. So this has been further elaborated. As you move close to the Earth's surface, the field lines come closer. You move towards the center, the field lines come even closer. That means the strength increases as you move towards the center. The field strength is higher because the field lines are close to the center. The field strength decreases as you move away from the center because the field lines move further apart. So we are saying the field is radial. The field is radial. So this is a simple conclusion. Most of these I have just been elaborating them and I've been explaining these ones. Okay, self-check. Self-check number one. Do everyday objects such as your pen have their own gravitational fields? Explain your answer. Do everyday objects such as your pen have their own gravitational fields? Explain your answer. I want somebody to explain that. I want somebody to explain that so that I can know that people have been following. Do everyday objects such as your pen have their own gravitational fields? If you are willing to give an answer, you tell us.
Yes, teacher.
Yes, explain.
Because pens have mass and the gravitational field is a region of space around mass.
All everyday objects that have mass therefore have their own gravitational fields. There is always a region of space around a certain mass where a force can be experienced. Therefore, the pens and any other everyday object which has mass must be having its own gravitational field. Any object which has mass has its own gravitational field. That was good of you, Cynthia. Is that Cynthia?
Yeah.
Okay. So that was a simple introduction to gravitation. That was a simple introduction to gravitation. Okay, so let's look at the force between masses. You might have been asking yourselves so many questions. We have seen that there is a force of attraction between two masses, but there are questions that you might be asking yourselves every day. Number one, what could be causing, what causes the weight that each of you feels? You might have asked yourself such a question. I don't know whether any of you might have asked themselves such a question. Kenny, what do you think causes the weight that you feel? Kenny, what do you think causes the weight that you feel?
Weight. It is due to gravity.
He says it is due to gravity. Precisely, the weight each of you feels is due to the gravitational attraction by the Earth. You might also, I'm saying the weight that you feel is precisely due to the gravitational attraction by the Earth. Number two, you might also have asked yourself such questions. What affects the size of the Earth's pull on you? Why would you weigh a different amount on the moon? What affects the size of the Earth's pull on you? And why would you weigh a different amount on the moon? Do we have Alpha on this in this class? Perhaps Alpha is absent. Mbabas, can you say something about that question? Do you ever ask such questions? Or is there a possibility that you would weigh the same on the moon? Isa, can you say something?
I feel like the force is less on the moon because we are further away from the Earth and we weigh less, but our mass is the same. Yeah, that's what I
Okay.
think.
So what affects the size of the Earth's pull on you? It is precisely it's because of your mass. Your mass is responsible for the size of the Earth's pull on you. Then the question is, why would you weigh a different amount on the moon? It's also because of the mass of the moon. The mass of the Earth is not the same as the mass of the moon. In fact, the Earth is many times bigger than, the mass of the Earth is many times greater than the mass of the moon. So the size of the Earth's pull on us will depend on our mass, and we would weigh less if we were on the moon because of the mass of the moon compared to the mass of the Earth. That means somehow the field strength is depending on the large mass. Somehow the strength of the gravitational field is depending on the large mass. Then the third question would be, if the Earth is pulling down on you, then what else must be occurring? Vanessa, can you say something about that? If the Earth is pulling down on you, then what else is occurring? Is it just pulling us downwards and that is all?
And there will be other forces like normal reaction, so it against the force.
I want you to be quoting a law so that we now know that you have developed in physics. You quote a law that you are referring to.
There must be some other force that cause you to resist the pull of the Earth.
You have not quoted any law. So by Newton's third law, you must also be pulling on the earth with a force equal to your weight. So if you are somewhere on the earth's surface standing, the earth is pulling on you towards its center. You are also, according to Newton's third law, I write N3 to mean Newton's third law, you are also pulling away from the earth's surface by an equal but opposite force, which Vanessa has called the normal reaction. You must also be pulling away from the earth's surface by an equal but opposite force. So the earth is not just pulling you downwards and that is all. You are also pulling yourself away from the earth's surface, according to Newton's third law. You are pulling away from the earth, or you are pulling up on the earth with a force equal to your weight. So the resultant is 0. And lastly, then what happens to the strength of the earth, of the pull of the earth, as you go further away from it? So this one we have just talked about it, that as you move away from the earth's surface, the field lines move further apart. So in other words, the strength of the pull of the earth as you go further away from it gets weaker. And I know most of you could guess this correctly from the incorrect assumption that in space, astronauts are weightless. It is true that as you move away from the Earth's surface, it gets weaker. And I know some of you have already read or have already got information that astronauts are always weightless in space. That is an incorrect assumption. They are not actually weightless, they just appear to be weightless. So as you move away from the Earth's surface, further and several kilometers away from the Earth's surface, the field is going to be weaker and weaker and weaker. So in summary, I'm trying to say that the force between two masses, or the force on an object in the Earth's gravitational field, depends upon the masses of the Earth and you. And it also weakens as the distance between you and the Earth increases. Isaac Newton showed that the Earth's force of gravity extends into space, but he showed that it weakens with the distance to what he called an inverse square rule. I think this is not the first time we are talking about the inverse square rule. The force weakens as you move away from the Earth's surface to what Isaac Newton called the inverse square law. What does that mean? It's like the force somehow follows an inverse relationship between two masses where F is the force and R is the distance between the two forces. The force follows what we call an inverse square law. So this means the Earth's force of gravity varies inversely with the square of the distance from the center of the Earth. This is what we now call, or this is what is called today, Newton's law of gravitation, or Newton's law of universal gravitation. We saw 3 laws, which were the laws of motion. Law number 1, Isaiah. Isaiah cannot state Newton's law number 1, Newton's first law of motion. Sandra, Newton's first law of motion.
Sure. An object stays in its original position unless an external force acted upon it.
An object stays in its state unless acted upon by a resultant external force. Law number 2, Mbabas. Perhaps she's off. Law number 2, Naomi?
Force is equal to mass times acceleration.
That is insufficient. Law number 2, Vanessa?
Force is directly proportional to acceleration and moves in the direction of the force.
Force is directly proportional to the acceleration. What do you mean? And moves in the direction of the force. Lisa, law number 2?
Law number 2 states that the acceleration of an object is directly proportional to the force and it moves in the direction of.
The net force is directly proportional to the acceleration. The net force and the acceleration are in the same direction. The net force is directly proportional to the acceleration. The net force and the acceleration are in the same direction. Law number 3, that is, Asen, can you tell us law number 3?
For every reaction, there is an equal.
Can you speak? Asen has gone.
For every reaction, there is an equal force, but in opposite direction.
For every reaction, there is an equal force, but in opposite direction. I think I mentioned that that statement is very insufficient because it does not actually state, it does not tell us that the action and reaction act on two different bodies. Whenever body A is in contact with the body B, body A exerts a force on body B and body B exerts an equal but opposite force on body A. I think that's what we mentioned as Newton's third law. Now we are talking about a new law in gravitation, which we are calling Newton's law of universal gravitation. Newton's law of universal gravitation. I said Isaac Newton showed that the Earth's force of gravity extends into space, and he showed from data that it weakens with the distance, and it follows what he called an inverse square law. The force follows an inverse square law. So, the force varies inversely proportional with the square of the distance from the center of the earth. And this is what we call Newton's law of gravitation. Whenever we have two masses that we are later on going to call point masses, there is a natural force of attraction between these two masses. This force varies inversely proportional to the square of their separation. This is what we call the inverse square law according to Isaac Newton, but is precisely called Newton's law of universal gravitation. So Newton's law of universal gravitation states that two point masses, I am calling them point masses to be specific, attract. The force between two masses is always attractive. Two point masses attract each other with a force that is proportional to the product of the masses and inversely proportional to the square of their separation. So the force between two masses, the force between you and the earth, depends on your mass and the mass of the earth, but it varies inversely proportional to the square of the distance between you and the earth, for example. Because when you move away from the earth's surface, the field strength decreases because the field lines move further apart. So the force weakens. So Newton's law of gravitation is telling us that one, the force between two masses, I will use F for the force, is directly proportional to the product of the masses. So I have M1 and M2. I have considered two masses, M1 and mass M2. And I'm saying, according to Newton's law of universal gravitation, The force between two masses, 1, depends on the product of the masses. Number 2, the force also is inversely proportional to the square of the distance between the two masses, or it is inversely proportional to the square of the separation between the centers of these masses. So when we combine these two expressions, it means the force is directly proportional to the product of the masses and inversely proportional to the square of the distance between the two masses. I may now want to take this expression further. By the way, the mathematics has started. So the force, I must remove the proportionality sign and introduce a constant. This constant, because we are dealing with the gravitation, this constant will be given a letter capital G. So F is going to be equal to a constant capital G, M1, M2 divided by R squared. The constant G is going to be called the universal gravitational constant. So G is going to be called the universal gravitational constant. This is a gravitational constant. So G is called the gravitational constant or the universal gravitational constant, and we shall see it later on. Now I want you to note, according to Isaac Newton, the force is equal to G M1 M2 divided by R squared. The force between two masses M1 and M2 depends on the product of their masses, these masses, and is inversely proportional to the square of the separation between the two masses. Now note that this force is always attractive. The force is always attractive. Sometimes a negative sign is put in front here. Sometimes a minus sign is put in front here. Following the convention, a convention is a rule. Following the convention that attractive forces are always given a negative, are always assigned negative values, and repulsive forces are always assigned positive values. So sometimes a negative is indicated here. This minus just indicates attractive, that the force between the two masses is always attractive. In calculation, we shall always ignore that minus. But later on we shall see where that minus cannot be ignored. So the force between two masses is directly proportional to the product of the masses and inversely proportional to the square of the separation between the two masses. I have referred to point masses. What is a point mass? Earlier on we saw that the field strength or the field lines due to the Earth were terminating towards the center. And we said for observations far away from the Earth's surface, you may assume that the Earth is a point mass. If I have a planet such as Jupiter and the Sun, can we say that Jupiter and the Sun can also be considered to be point masses? I want you to note, Newton's law of gravitation only applies on point masses. Newton's law of gravitation is only applicable on point masses. What are point masses? Can we consider the Earth and the Sun 2 point masses? To you, the word point indicates very small, which is very true. But if two objects, however large they are, have a separation between them which is far, 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 far bigger than the diameter of n of the masses or the radius of n of the masses, the two masses can still be called point masses. If the distance between Jupiter, the largest, I think it's the largest planet, and the Sun, which is so many times larger than all the planets, if the distance between Jupiter and the Sun is many times bigger than the radius of the Sun, or the diameter of the Sun, or the diameter of Jupiter, it means Jupiter and the Sun can be considered to be point masses. So two masses are said to be point masses if their separation is much larger, much greater, or much bigger than the diameter of any of the two objects. So Newton's law of gravitation is only applicable to point masses. And I've explained what we mean by point masses. Coming back here, we can first of all establish the units of this constant here, making the constant g the subject. G is going to be Fr squared divided by M1, M2. I've just made G the subject. I think that is correct. So when you try to play around with the units, I'm trying to establish the units of G. F is newtons, R is meters squared, then mass times mass, that is going to be kilograms squared. So it means the units of G will therefore be newtons meters squared per kilogram squared. This is not SI, I mean base units, but these are just the units. So G, the constant G is called it is called the universal gravitational constant, which has normally units as newtons meters squared per kilogram. By the way, the value of G is normally given in the list of constants, in the list of data, and G has a value which is approximately 6.67 times 10 power and negative 11 newtons meter squared per kilogram. So the universal gravitational constant is always quoted as 6.67 times 10 power negative 11 Newton meter squared per kilogram squared. This is per kilogram squared. So this is according to Isaac Newton. From the data obtained by Isaac Newton, he was able to come up with this gravitational constant, and we shall not go into details about how to come up with this gravitational constant. So I want us to make a few points, to note a few things from what we have just seen. Number one, we have seen that the force between two masses follows the inverse square law. And the inverse square law is stating that the force between 2 point masses is directly proportional to the product of the masses and inversely proportional to the square of the separation between the two masses. So, number one, this law is only applicable if M1 and M2 are actually point masses. Every time I use this law, I have made an assumption that the two masses are point masses. At some point, we shall mention that if the two masses are not point masses, then the law is not applicable. Number two, normally we assume that the masses we are dealing with are spherical in nature. And if the masses we are dealing with are spherical in nature, first of all, we are assuming that their density is uniform. The density is uniformly distributed. But note that some parts of the Earth, for example, which are rocky, may have a slightly different density compared to other parts of the Earth. But whenever we use the expression F is equal to Gm1 m2 over r squared, we assume that the density of the object that we are dealing with is uniformly distributed. And also by using this expression, we are assuming that the object is a perfect sphere. Because if it's not a perfect sphere, then the field lines are not radial. And if they are not radial, then they don't move apart as you move away from the center of the object. So every time we use Newton's law of gravitation, we are assuming that, one, we are dealing with 2 point masses. I said two masses are point masses if their separation is much greater than the radius or diameter of each mass. And of course, a point mass has a radial field, as we have seen with the Earth. So their density is going to be assumed to be uniformly distributed, and the two masses are going to be assumed to be perfect spheres, especially if the bodies are rounded. For example, if we consider the Earth. So, although the Earth is a large object, on the scale of the universe, it can be considered to be a point mass, because compare the Earth and the universe as a whole. the gravitational field strength at its center is 0. We have already seen that the gravitational field strength is also going to depend on the mass. But at the center of the Earth, then the mass is 0 at the center. So it means if you are at the center of the Earth, you don't experience any force due to the Earth. So the field strength at the center is going to be 0. We have also seen that since attractive forces pull equally in all directions, then if you are standing at the center of the Earth, then the resultant force on you is going to be 0. So beyond the Earth or beyond the surface of the Earth, the gravitational force is actually decreasing with increasing distance, that is following the inverse square law. If the distance doubles from the center, for example, if the distance is twice the original or is twice the radius of the Earth, then it means the force actually will increase, I think, by a different, or the force decreases by, I think, 1/4 of its original value. If the distance doubles, the force decreases by 1/4 of its original value. That means if we were to sketch a graph, of the variation of the force with the distance from the center of the Earth, if we were to sketch a graph with the distance from the center of the Earth, then we would have such a graph. I'm just looking at the surface. Let this be, I'm going to consider this to be, let's just look at the surface of the Earth, because literally you may not easily enter deep into the Earth. So this is at the center of the Earth where G is 0. This R is standing for the radius. So as we move away from the Earth's surface, because the force is varying as inversely proportional to the product of the masses and to the square of the distance. As R increases, the force F decreases with a very significant factor. Initially, if R is capital R, we notice that the force in this case is going to be a constant G, m1, m2 divided by R capital R squared. If the distance is twice R, then the new value of force is going to be Gm 1 m2 divided by twice R, but this is squared. And this gives us G m1 m2 divided by 4 R squared, which is the same as 1/4 of the origin of the force at the surface. So because this is 1/4 times the original value G m1 m2 over R squared. So it means as we move away from the Earth's surface, the value of the force decreases because the force varies inversely proportional to the square of the distance between two masses. So this force between the two objects, which is due to gravity, is actually reducing as the distance separating the two objects increases. What does that imply? We can therefore predict that finally at infinity, perhaps the force becomes 0. At infinity, we can predict that the force becomes 0 because F is going to be equal to G m1 m2 divided by the distance is now infinity and squared. At infinity, then the force will be tending towards 0. So it means when you go far away from the Earth's surface, then the force on you due to the Earth's pull tends to 0. But you should be far enough for that force to be significant. You should be far enough for that force to be significant. Oh, I think we can do some examples before we sign up. Example number one. I hope we are all at the examples. The masses of the Sun and the Earth are 2.0 times 10 power 30 kilograms. That is for the Sun, and the Earth is 6.0 times 10 power 24 kilograms, respectively. Their separation is 1.5 times 10 power 8 kilometers. Calculate the force of attraction between the Sun and the Earth. Calculate the force of attraction between the Sun and the Earth. I'll use this space for the solutions. I hope it will be enough. So here we are just going to use Newton's law of gravitation, where the force between two masses depends on the product of the masses, m1, m2, divided by the square of the separation between the two masses. We want the force. So I'm just going to substitute. Remember, G is called the universal gravitational constant, which is 6.67 times 10 power negative 11. Product of the masses, 2.0 times 10 power 30 times 6.0 times 10 power 24 divided by the square of the separation between the two masses. You notice that the distance given is in kilometers, so I have to change it to meters. And that in meters becomes 1.5 times 10 power 11. And this should be squared. Somebody press the calculator and tell me their answers. I know some of you are in this class and we don't have calculators. You are just enjoying. But be informed that I'm not repeating this content in school. That one I'm very sure. I'm waiting for someone to press the calculator and tell me the answer.
3.6 times 10 power 22.
So this is 3.6 times 10 power 22 newtons. Okay, so that is the force of attraction between the Sun and the Earth. It means the Earth is pulling the Sun with this force. The Sun is also pulling the Earth with the same force. That is according to Newton's third law. The Earth is pulling the Sun with that force. The Sun is pulling the Earth with that force. Example number two. The mass of the dwarf planet Pluto. I think Pluto is no longer a planet. I must have mentioned that some time back. The mass of the dwarf planet Pluto is approximately that. Calculate the force of attraction between Pluto and the Sun when their separation is 5.9 times 10 power 9 kilometers. We can use the same value for the mass of the Sun. Calculate the force of attraction between Pluto and the Sun when their separation is 5.9 times 10 power 9 kilometers. Okay, so I'm going to rub off this. I want to use the same space. So I will erase this and I use the same space. So we want to find the force of attraction between Pluto and the Sun. So force is equal to the gravitational constant, product of the two masses, divided by the square of the distance between the two masses. So this is going to be 6.63 times 10, no, not 63. I'm remembering Planck's constant. So it is 6.67 times 10 power negative 11. That is the gravitational constant, which is always given. Product of the masses, 1.2 times 10 power 22 times the mass of the Sun. We shall use that as the mass of the Sun because it is a constant, 2.0 times 10 power 30 divided by the radius. R is the distance, the separation between the two. Because this is given in kilometers, I will change it to meters. So this will be 5.9 times 10 power, I think that would be 12, but this should be squared. You can press your calculator to check if this is correct. I think maybe this is times 10 power 16.
It's just
4.6
times 10.
yeah.
Times 10 power 16.
Yeah.
Okay, now Number 3 is yours. I'm waiting for your answers. Estimate the gravitational force of attraction between two people sitting side by side on a park bench. How does this force compare with the gravitational force exerted on each of them by the Earth? That is their weight. First of all, just tell me the estimate of the force between two people seated side by side on a park bench. We studied the estimates, so this should not be something very strange. If you have come up with an answer, you raise it so that we save time. Anybody who has come up with an answer? Anybody who has come up with an answer?
Teacher, I think that the gravitational force exerted on both of them will be the same. Because
I
even
want
though
the
they are
estimate
seated
first.
side by side,
What is the estimate?
that I do not know.
Estimate the gravitational force of attraction between two people sitting side by side on a park bench. Anybody who came up with an estimate? Anybody who has come up with an estimate?
2.4 times 10 power negative 5 Newton.
Times 10 power negative 5 newtons. Okay, so the force of attraction between two masses is given by G m1 m2 over r squared. So when we estimate the G is 6.67 times 10 power negative 11, we estimate the masses. Masses of two people sitting side by side. You can't fail to estimate the masses of people. So we can say one person is maybe 70 kilograms, the other one could be 80 kilograms. Those are estimates. Divide by the separation between the two, whatever distance, because it is just a park bench. You have seen benches in the park, side by side. You could even estimate this to be 1 meter aside, 1 meter apart, even if you estimate to be 2 meters apart. So let's say this is 2 meters. It is just an estimate. So I press my calculator. You can also press yours. 70 times 80 times 6.67 exponent negative 11 divided by 4. So you can find your answer. Me, I'm getting around 10 power negative 10 power negative 8 newtons. I don't know whether you're also getting the same. around 10 power negative. If you have estimated somebody to have 100 kilograms, perhaps you'll get another power, but it is close to 10 power negative 8.
Yeah.
So that is my estimate, 10 power negative 8, whatever digit is in front there. Then how does this force compare with the gravitational force exerted on each of them by the Earth? That is their weight. So if we try to find the weight of each of these person, let's just find the weight of one of the people, or one of these people. So weight is going to be mass times g. So this mass, let me say 80 kilograms times 9.81. So if you try to find this weight, what is that weight? 9.81 times 80.
784.8.
So now you notice that the weight, which is the force exerted on the people due to the gravitational force, is far, 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 far greater than the force of attraction between them. The weight exerted by the Earth on these people, which is the gravitational force between the person and the Earth, the gravitational pull between the person and the Earth, is far, far greater than the gravitational force between the two masses. The weight is far, far bigger than the gravitational force between the two masses, or between the two people. In fact, you would notice, you would even come up with a factor. By how many times is the weight bigger than, by how many times is the weight bigger than the force between the two masses of the people? Just divide this by that factor, and you'll get about 10 power 10. So the weight is about 10 power 10 times bigger than the force between the two people. The weight of the Earth, or the force caused by the Earth onto these people on each of these, is about 10 times, 10 power 10 times the force caused by one person on another person. So it means whenever we have two objects very close to each other and they are not point objects, because their separation is not infinitely large, then the gravitational force between them is going to always be extremely small. Maybe we can do one more example for now. Calculate the gravitational force of attraction between them. Two objects separated by a distance of 1 centimeter. I think this one you can calculate, and each having a mass of 100 grams. Please calculate very fast. You tell me what you get. We have only 5 minutes remaining.
For question A, it is 6.67 times 10 power negative 7.
She's saying 6.67 times 10 power negative
7.
7. I hope you changed the mass from grams to kilograms. And I hope you changed the distance from centimeters to meters.
Not, I didn't change it.
So that
6.67 times 10 power negative 9 Newton.
So this would be negative 9 newtons. When you change the units, that would be times 10 power negative 9 newtons. Okay. Part B. You have two asteroids separated by a distance of 4.0 times 10 power 9 meters, and each having a mass of 5.0 times 10 power 10 kilograms.
I got 1.0 times 10 power negative 8.
She says she got 1.0
0 times 10 power negative 8.
times 10 power negative 8 newtons. Okay, and then the last part, I think that is correct. The last part, a satellite of mass 1.4 times 10 power 4 kilograms orbiting the Earth at a distance of this from the Earth's center. The mass of the Earth is given as that. Calculate the gravitational force of attraction between a satellite and the Earth. What are we getting?
Should we change the kilometers to meters?
Yeah, of course you can't get the force in newtons unless all the quantities are in their SI units.
The answer is 1.2 times 10 power negative 17.
Times 10 power negative, that is a very small force.
Teacher, I got power negative power 18. Power 18.
Power 18.
Yeah.
Okay, but I'm doubting. So the force is equal to 6.67 times 10 power negative 11, that is G, capital G, the gravitational constant. 1.4 times 10 power 4, then times the mass of the Earth, 6.0 times 10 power 24, divided by the square of the separation, which is 6,800. When I change from kilometers to meters, I'll add 3 zeros, and this is squared. That power 18 is too big.
What about 1.2 times 10 power 5?
Power 5. I think this is correct.
Okay.
I think that is correct. Okay, so that is actually the introduction to gravitation. In summary, or to wind up today's lesson, we have seen that we shall study three types of fields. We say that field is a region of space where a force can be experienced. A region of space where a force can be experienced. This region can be due to a mass, and if it is due to a mass, it is called a gravitational field. That region of space around a mass where a force can be experienced is the gravitational field. I mentioned that we shall also see electric fields, we shall also see magnetic fields. We said fields are represented by lines, and the arrows show the direction of the field. The spacing between the arrows, between the lines, shows the strength of the field. We saw that the field strength due to the Earth is radial. The field lines point towards the center of the Earth. As you come close to the Earth's surface, the field is stronger. When you move away from the Earth's surface, the field is weaker. But we said on the scale of a building is something small compared to the Earth. On the scale of a building, your weight will still be the same on the bottom floor as on the top floor, because the change in the height on the scale of a building is always very small. So the change in the field strength is very small. In fact, we mentioned that the field lines are almost parallel to each other. Therefore, the field appears as if it is uniform, and therefore the field strength is considered to be constant. That is on the scale of a building. Then we said that the force between two masses follows an inverse square law according to Isaac Newton. The force between two masses follows an inverse square law according to Isaac Newton. In fact, force is directly proportional to the product of the masses and inversely proportional to the square of the separation between the two masses. But I said this law only applies to point masses. I said two masses are considered to be point masses if their separation is much greater than the size of any mass, if their separation is much greater than the diameter or the radius of any of the two masses. So according to Isaac Newton, the law of gravitation or the law of universal gravitation states that two point masses attract each other with a force that is directly proportional to the product of their masses and inversely proportional to the square of their separation. So we have done a few examples, and I think we are now good enough to go. We have seen that the graph as we move out from the surface of the earth just indicates a decrease in the force, and we mentioned that therefore at infinity the force is most likely going to be zero or tending to zero from the earth. As you move to infinity from a certain mass, the force becomes very, very small. We posed a serious question that I want us to always recall, that why don't we see two objects in our everyday life moving towards each other when they are side by side? We have seen that the force between the two masses could be very, very small, that other forces could be preventing the two masses from moving towards each other. These other forces could include friction. I think that is a good conclusion. So I hope we should hang up at this point